Hello there, Mr. Sutton here, bringing you these AB Calculus 611 Extra Practice number 4 solutions on accumulation and rate in, rate out free response practice. For this calculator-based free response problem, we have the depth of a tank A modeled by some differentiable increasing function h, and this is on the time interval 0 to 10. We don't know exactly what h does, but we've got a few table values up here for h. Now, based off of this, our first task is to use the data in this table to find an approximation for h prime of 6. Okay, so we can't find the exact value of the derivative of h at 6. We can't find the instantaneous rate of change at 6 because we don't know what h looks like algebraically. However, we can use some values of h to find an average rate of change for h, and we'll just do that on an interval that includes 6. So a good interval to use would be 5 to 7, because 6 is right smack dab in the middle of that. So I'm going to say then that h prime of 6 is approximately equal to, and now we're doing average rate of change here, we're going to have h of 7 minus h of 5 over 7 minus 5. So that's going to be 18.5 minus 15.5 over 7 minus 5. And I'll just do that on my calculator now. Although, actually, I don't really need the calculator just yet. It's a calculator problem, but I got this. So in the numerator, we have 3. Denominator is going to be 2, so that's 1.5. And our units, since we're doing basically h over t here, we're going to have inches per minute. So 1.5 inches per minute. For this part of the problem, they want us to approximate the integral of h of t from 0 to 10 using a right-Riemann sum with the subintervals indicated by this table. So I'm going to write that this integral is approximately equal to the following, and I do need to write approximately equals here. So I'm going to have 4 rectangle areas that I'm adding together, base times height kind of deals. For the base, I just have the distance between the minutes here, and for the heights, I have these output values. But now, each rectangle has 2 choices for the height. This first rectangle, for example, from 0 to 2, we have a base of 2, and we have a left height and a right height. Since it's a right-Riemann sum, we're going to use the right height each time around. So I have a base of 2 times a height of 10 for that first rectangle. Plus, the next rectangle, we have a base of 3 from 2 to 5 times a height of 15.5. After that, we have a base of 2 times a height of 18.5. And finally, a base of 3 times a height of 20. And I will just use the calculator this time around to add all these together. So letting the calculator crunch all those numbers, we end up with 163.5. And in terms of units, we just integrated the height here. So what units would that even be? Well, we have the h function here is inches. dt has the time units, so that's minutes. So this is going to be 163.5 inch minutes, whatever that means. So now the more important question, because I'm not sure that units were actually required there. They didn't say indicate units of measurement. This next part, though, is this approximation greater or less than, and this is basically saying the true value of the integral of 0 to 10 of h of t dt. So this is all going to depend on whether or not you have an increasing or decreasing function and what kind of RAM you're dealing with. Since this is an increasing function on the interval from 0 to 10, and this is our RAM that we're dealing with, that means that this approximation, 163.5, is actually going to overestimate the true value, so it's going to be greater than the integral from 0 to 10 of h of t dt. For this problem, we're given the depth of water in tank B as this g of t function. And the first task on this part of the problem is we want the average depth of the water in tank B over the interval from 0 to 10. So we're going to have 1 over the interval length, so 1 over 10 minus 0, and this is giving me average depth for tank B. We're going to multiply that by the integral from 0 to 10 of this depth function, the g of t, and I'll have a dt in there. Let me do that on the calculator. So on my calculator, I've entered the g function in as y1 and my y equals. Let me quit out of there, and I'll do, let's see, fancy fraction, 1 over 10, times my integral, so math 9, from 0 to 10, and we'll do alpha trace y1, because that's where I stored g of t, dx, and all that's going to come out 2, and it's going to take a few seconds on this one, But if we wait patiently, we see that all of that comes out to an average depth of 16.624. And that's going to be in inches because it's the same units as the original. Okay, so that's tank B, but there's a little bit more to this problem. They want to know if this value is greater than or less than the average depth in tank A. So tank A's depth is going to be kind of the same setup, 1 over 10 minus 0, because it's the same interval here. And then we have 0 to 10 for our integral, so same as before. But the depth function for tank A was h of t, not g of t. So this is going to be h of t dt. And here we run into a little bit of an issue because we don't know what h of t actually is algebraically. So we can't use our calculator to come up with a value like we did for g of t. But we have a little bit of a way around this. So you might remember back in part B, which I'll go back to now. Here's part B again. We were asked to approximate the value of the integral from 0 to 10 of h of t dt. And we did that using a right-Riemann sum, and we found that that value was 163.5. So fast forwarding, since we already know an approximate value for h of t evaluated from 0 to 10, we can say that our average depth is, I guess, approximately 163.5 over 10, which is to say 16.35 inches. So just looking at these, they were asking if the tank B value was greater than or less than the tank A value. And here it certainly looks like tank B has a greater value. We can't conclude that just yet, though, because this tank A value we got, we used an approximation for this numerator. And that means that the whole thing is really an approximation that, for all we know, might be greater than or less than this other number. I mean, we don't really know unless we do a little more analysis. So here's where we have to look back at another part of part B, where they asked, is this approximation greater than or less than the actual integral from 0 to 10 of h of t dt? And we concluded that the 163.5 was greater than the true value. Another way of saying that, going back to part C now, is that this true value here is less than 163.5. The true value of this integral is less than our approximation. What that means is that the true average tank depth is also going to be less than our approximation of 16.35. So tank A's average depth is less than 16.35. 16.35 itself is less than 16.624. So the over-approximation for A, even though it's an over-approximation, still doesn't even beat out what we had for tank B. So based off of this, we can conclude beyond any shadow of a doubt now that tank B has a greater average depth than tank A. For the last part of this problem, according to the model in part C, that was that G function that they gave us. Is the depth of the water in tank B increasing or decreasing at time 6? Well, what we're basically asking, since G is the depth of the water, they're asking, is G prime positive or negative at time 6? So we're basically just doing G prime of 6 and looking at the sign of this thing. The good news is, since they already defined G for me back in part C, I don't have to actually figure out the derivative of G algebraically. Since I'm just taking the derivative at a specific point, I can just use the derivative function on my calculator with the original function and just give you the answer. So let me go ahead and do that. So here we are back on the calculator. And just to review from part C, this is y1, where I put my g of t function. So this is g of t right here. Quitting out of there now, let me do math 8 to pull up a derivative. And I'm going to do dx. In here, I'm going to do alpha trace y1 to put g of t in there. So now I'm figuring out g prime. And I'm going to do that at the value 6. So that ends up giving me 0.887. Now that's a positive number. Since the derivative of g is positive at 6, that tells me that the g function, and thus the depth of the water in tank B, is increasing at time 6. For this calculator-based free response problem, we have a zoo sponsoring a one-day contest to name a baby elephant. Zoo visitors deposit entries in a special box between noon, which is time 0, and 8 p.m., which is, well, time 8. And the number of entry in the box t hours after noon is modeled by some function e, which we're not going to tell you at this point, other than the fact that some values of e of t are up here in this table. So this is hundreds of entries we're measuring this in as a function of hours. And now based on all this, our first task is to use the data in the table to approximate the rate in hundreds of entries per hour at which rates are being deposited at time 6. So we're basically trying to figure out E prime of 6 and estimate that. Since I can't figure out the instantaneous rate of change of E at 6, I'm going to approximate that, like they said, with the average rate of change on an interval that includes 6. So I'm going to do average rate of change for E over the interval from, let's say, 5 to 7. 6 is right in the middle of all that. So I'm going to do E of 7 minus E of 5 over 7 minus 5. And I'm going to say that E prime of 6 is approximately equal to this. So that's going to be 21 minus 13 over 7 minus 5, which, let's see here, that's 8 over 2, which reduces to 4. So this is going to be 4, and the units are going to be hundreds of entries per hour, because I have E over T, basically. For this next part of the problem, they want us to use a trapezoidal sum with 4 subintervals given by the table to approximate 1/8 times the integral from 0 to 8 of E of t dt, and then basically explain what we just did. All right, well, let's deal with the more numerical part of it first. So this is going to be approximately equal to 1/8 times, and now I'm going to open a big old parentheses here. So I'm doing trapezoids. So these each have a setup of base 1 plus base 2 over 2 times the height. So for my first trapezoid, going from 0 to 2 here, I have a base of 0 plus a base of 4 divided by 2 over the height of 2, and I get the height by just finding the distance between the times here. And then next I have a 4 plus 13 over 2 times a height of 3. Then 13 plus 21 over 2 times a height of 2. And finally, 21 plus 23 over 2 times a height of 1 from 7 to 8. I don't have to simplify this, but I'm going to, so let me do that on the calculator. So I just took a little time and very generous use of alpha y equals to get my fancy fraction mode here. I entered that whole thing on there, exactly like I wrote it down there, and pressing enter, that comes out to some crazy fraction. Let me do math, and then second option there, decimal, to see what decimal that is. So that comes out to about 10.688. And the units on this, since I took basically the average value of E, and E was in units of hundreds of entries, this is going to be 10.688 hundreds of entries. Now, what did we just do? Well, what we were multiplying here, this 1/8, this was actually 1 over the interval length. When you do 1 over the interval length times an integral of something, you're essentially finding the average value. So this was the average number of entries in units of hundreds of entries over the time interval from noon to 8 p.m. or time 0 to time 8 hours. For this part, at 8 p.m., volunteers begin to process the entries. I guess you can't just leave them in the box. They process the entries at a rate modeled by the p function here, which is some cubic polynomial, and this is hundreds of entries per hour between the hours of 8 and 12. According to the model, how many models had not yet been processed by midnight? All right, so we have to talk about basically the number that we're starting with at 8 o'clock minus the total processed between the hours of 8 and 12. So our unprocessed entries, we're starting with, at 8 o'clock it says in the table here we have 2,300 unprocessed entries. And we're going to subtract, now the number processed over those 4 hours, you've got the rate at which things are processed. So you just need to take the integral of the p function between 8 and 12, and that'll tell you how many entries actually get processed over that time period. And then we just have to subtract that from the amount we're starting with. So we're going to have 23 minus integral from 8 to 12 of p of t dt. And since p is already defined here, we can just do the rest of this on the calculator. To make things a little bit easier to process for myself, I'm going to put this p function in my y equals under y1. And then let me quit out of there, and I'll do 23 minus the integral. So this is going to be math 9 from 8 to 12. And I stored that in y1, so I'm going to do alpha trace y1. That's really p of t going in there. And now we have an x that I always put in there. Press enter, and that comes out to exactly 7. Well, that's nice. So that's going to be 700 entries that had not yet been processed by midnight. For this last part of the problem, according to the model from part C, which I put up here so we can refer back to it, this was again p of t, the rate at which entries are processed between the hours of 8 and 12. So based on that, at what time were the entries being processed most quickly? So essentially, we're asking at what time does p reach its maximum value? That's really what it boils down to for this. So to figure out the absolute max time for p, we're going to use the candidates test. We're going to test out the endpoints, which are the hours of 8 and 12, and we're going to test out any critical values. Specifically, I'm going to test out local maxes. So to find local maxes, I first have to take the derivative of p and graph it out. So p prime, that's going to be 3t squared minus 60 plus 298. And now I have to see when this equals 0, but specifically I want to see when this changes from positive to negative. So let me go and find that on my grapher. So to do this, I'm going back to my y equals, and in y2 I've put p prime, the derivative of p, and I've deselected the p function up here because I don't want to graph that too. I just want to graph p prime, and I want to graph it on a window from 8 to 12. So make sure you've got that window in there. So let me do zoom 0, zoom fit. So here's p prime. Now there's two places where we're crossing the x-axis. However, I'm not interested in both of them. If I'm looking for the maximum value of p prime, then, or the maximum value of p, I should say, then all I care about are local maxes in terms of these critical values. So p prime is only changing from positive to negative in one spot. This spot right here, whatever this is. So let me do second trace, and then 0. And then let me move my spider a little bit to the left of that intersection. There we go. Press enter. A little bit to the right. Press enter a third time. And let's see, that happens at about 9.184. We'll say 35. We'll just take it to 4 decimals. So there's my picture, and I'm actually going to call that A, just so I can refer back to it quickly. So let me go to my calculator. Let me quit out of there. And I'm going to press the store button, and we'll store that as alpha A. All right, so now I can pull that back whenever I need to. Now notice my wording here. P prime changes positive to negative only at A equals all this stuff. So that's basically telling people, hey, I'm only going to consider critical values that are local maxes. There may be other ones. I don't care. None of them matter. Only this matters. So that basically gets me off the hook from testing out this other critical value when it comes time to do the candidates test. I'm saying out of all these critical values, A is my only candidate. All right, well, it's time to test out all the candidates now. So I'm going to start by testing out 8. That was the left endpoint. So to do that, I'm just going to go back to my calculator, and I'm going to do alpha trace y1. That's where I stored the p function. I'm testing all of these in p now, the original function. And I'm plugging 8 into that. Comes out to 0. So let's write that down. And next, I'm going to test out time A. So going back here. Now this gets a little bit easier as I go. I'm just going to yank my input from before, and I'm going to replace 8 with A. Press enter. Comes out to about 5.089 and some change. So that's definitely better than 0. Let's test out midnight as well. So yanking my input from before, let me replace A with 12. Enter, and that comes out to exactly 8. So out of all of these, 8 is the highest value. What this means in real life is that our entries are being processed most quickly. The rate of change is greatest at midnight. For this calculator-based free response, the rate at which water flows out of a pipe in gallons per hour is given by a differentiable function R, and we've got a table showing the rate R as measured every 3 hours for a 24-hour period. So we've got some random values or semi-random values in there. Our first task is to use a midpoint Riemann sum, MRAM, for subdivisions of equal length to approximate integral from 0 to 24 of R of t, and then explain what we just figured out. Okay, so if I have 4 subdivisions of equal length to get from 0 to 24, that means my subintervals have to have a distance of 6. So I'm going to say that my integral here is approximately equal to the following. So these are all going to be base times height rectangle areas. So each of these is going to have a base of 6, and the height is going to be the output value of the middle input. So I've got a base of 6 for the first rectangle that takes us from 0 to 6, times a height of, I'm going to use 10.4 because that's the middle value, and this is a midpoint Riemann sum. So 6 times 10.4 plus, next rectangle from 6 to 12, we have a base of 6 times a height of, now we have to use the value at 9, so 11.2. Now then we have a base of 6 times a height of 11.3, and then base of 6 times a height of 10.2. Let me go ahead and do that on my calculator. Now on my calculator, since these subdivisions were all of equal length, since these were all basically 6 times a number, I just basically factored a 6 out of all that and did 6 parentheses and then all of the heights added together to give me a total of 258.6. And since I took the integral of rate of flow here, gallons per hour, basically multiplied that by hours, that's what the units on dt is, so that just ends up canceling out the time units and giving me gallons. So I have 258.6 gallons. What this means is that from 0 to 24 hours, and we have to mention the time interval here, 258.6 gallons flow out of this water pipe. For this part of the problem, we're asking if there's some time between 0 and 24 such that r prime equals 0. So if we have information about the original function and we want to guarantee a certain value about its derivative, we need to use the mean value theorem. So to use this, I have to show that my function, my original function, r of t, is continuous on the closed interval from 0 to 24 and differentiable on the open interval from 0 to 24. In the beginning of the problem, they said that r was a differentiable function. They didn't specify an interval, so that means r is differentiable everywhere. And if r is differentiable everywhere, it is continuous everywhere. Therefore, I'm going to say that r is continuous and differentiable on the closed interval from 0 to 24. So if it's differentiable on a closed interval, then we've got the open interval for free. So that means I can use the mean value theorem. So to actually use this, I need to take the average rate of change from 0 to 24 of r and show that it actually equals this value I'm looking for, this 0. So let me do, let's see here, this is going to be r of 24 minus r of 0 over 24 minus 0. R of 24 in our table is 9.6. R of 0, also 9.6. So we have 9.6 minus itself over 24 minus 0. And this is just 0 over something that's not 0, so that comes out to 0. Therefore, by the mean value theorem, we've just shown that r prime of t has to equal 0 somewhere on the open interval from 0 to 24. For the last part of this problem, the rate of water flow r of t can be approximated by this q of t function. So now they're actually giving us something that tells us what's going on with r of t. We want to use this q of t function, the qt function, to approximate the average rate of water flow during the 24-hour period. Okay, well, if I want to approximate the average flow then, what I'm going to do is use my average value setup. So that's going to be 1 over the interval length, so 1 over 24 minus 0, times the integral from 0 to 24 of the thing I'm trying to average. So I'm just going to write qt dt in here because they already told me what qt is. And note that I said average value is approximately equal to, because they didn't say that qt was r of t. They said it was an approximation of it. So let me go ahead now and do this on the calculator. So on my calculator here in the y equals, I put the q of t function in as y1. Let me just quit out of that, and I'll do, let's see, alpha y equals, fancy fraction mode. We'll do 1 over 24. and then we're going to multiply that by the integral, so math 9, from 0 to 24. In here I want to put my q of t function, so alpha trace y1, because that's where I stored q of t, and then dx, press enter, and hope for the best. So that comes out to 10.785, and that's going to have the same units as the r of t function, which they set up here was gallons per hour. So 10.785 gallons per hour.